Hello, so welcome to another video where we will be looking at some properties of solutions, and specifically here we will look at how a solution reacts to when a gas is dissolved in it, or actually when or how much gas can be dissolved in a solution depending on the gas's pressure. So I mean, it makes sense. So if you apply more pressure, a gas should be dissolved more in a solution, or at least more in a solvent than when there's less pressure applied. So in this case, we're looking at a closed bottle of soda water, which it says has a headspace pressure of 5 atmosphere at a specific temperature, and the Henry law constant is certain mole per liter per atmosphere. Determine the solubility of the gas in mole per liter in the closed bottle, and then the second question, but we'll look at that. But let's just first analyze what's going on here. And of course, headspace, if you might not, for example, know what that means. So if we have our little soda bottle here, so we give it a little cork, and we have a bottle of some sort, and the bottle is filled with water, then headspace refers to this part where the water is not, so meaning the top part of your bottle that has the gas, meaning the air or whatever, if it's carbonated water, in other words, assuming that it's mostly then carbon dioxide. And it implies this means the closed bottle here has a pressure of gas, or just abbreviated PG, equal to 5.0 atmosphere. Okay. We also know then the temperature, but that doesn't really influence something. It just basically says it's a constant temperature. So that means there's not going to be a difference, or the pressure is not going to change, because the pressure of the gas is dependent on the temperature. If we increase the temperature, the pressure should also increase. Right, so we know the pressure of the gas. And we want to know how much gas is then actually dissolved, or at least then in what is the solubility of the gas in mole per liter. But what is mole per liter? Mole per liter is a concentration unit. It is a certain amount of substance, mole per liter, so per solvent, it is the same as dissolving sodium chloride in water, or sodium hydroxide, or HCl in water. All those concentrations units you've been constantly with, it's molarity essentially. It's mole per liter is molarity at the end of the day. So that's what the solubility of the gas is. So it's just asking us, what is the molarity of the gas given its pressure in the closed container? Right, and how we calculate that is using that Henry constant for the gas. So the Henry constant for the gas gives us an indication of, at a specific pressure, what will be the concentration of the gas in terms of molarity. Right. And it's independent of solvent and all those kind of things. So how we write it is we say solubility of gas, and it is abbreviated as Sg, equals to the Henry constant multiplied by the pressure of the gas. As simple as that. So that's 3.1 multiplied by 10 to the minus 2 mole per liter per atmosphere. And the pressure of the gas is 5.0 atmosphere. That gives us a value of 15.5 times 10 to the minus 2 mole per liter. And let me just check, 0.2, so it's two significant figures. So it says mole per liter, so we can round it to 16. So 16 times 10 to the minus 2 mole per liter. Maybe just write for yourself. This is 0.16 molar, or 0.16 times 10 to the minus 2, or 0.16 mole per liter as well. Right, and that gives us the molarity of the gas. In other words, how much gas is then, how much of this CO2, so there's of course CO2 on top here, but there's of course CO2 trapped in the water as well. That's why your gas is, or your soda water is fizzy. And of course, this is also this is for the A part of the question. So let's look at the B part. The B part now says, determine the solubility of the gas in the bottle after it has been standing open to the atmosphere for some hours. The partial pressure of CO2 in the air under these conditions is so much bar. So of course, this now means the pressure of the gas has changed. And we're also now given the pressure of the gas in bar. So don't let the part of the partial pressure of CO2 is under these conditions is that, because we're interested in what is the solubility of CO2. We're not interested in the solubility of all gas in the water. There's also going to be some oxygen now and some nitrogen and other gases dissolved in the water, but we're principally interested in CO2 solubility. And CO2 solubility is connected to its pressure, which is connected to its partial pressure. So we first need to determine what the pressure is of the gas. So that is going to be this 4.05 times 10 to the negative 4 bar, which is 0.9869 atmosphere per bar. So we're just taking it to atmosphere because all our units, if you check for the Henry constant, everything is in atmosphere. So we just want to get our pressure unit in atmosphere, get a value of 3.99 or times 10 to the negative 4 atmosphere. And so you see the solubility of the gas is going to decrease slightly. So K Henry multiplied by the pressure of the gas is still this 3.1 times 10 to the negative 2, because Henry, the constant, is dependent on temperature. So the constant will increase depending on higher temperature or decrease with the temperature. Mole per liter per atmosphere multiplied by this 3.99 times 10 to the negative 4 atmosphere. That's going to be two significant figures, 1.2 times 10 to the negative 5 mole per liter, or 1.2, we can also put it as what? 0.12 times 10 to the negative 6, just to compare it with the 0.16 molar that we have on top there. And if we compare those two values, then we can see, of course, the one where the bottle is closed versus the one where it's open is, of course, much lower. And I mean, that makes sense because in this case, of course, our drink is so-called when we call it flat. I mean, that's why your soda drinks or your soda water or whatever, when you open it for a long time, it goes flat because your gas leaves your drink, all the gas starts to evaporate, the solubility of the gas decreases, or technically the concentration of the gas decreases in the water because it is allowed to escape, because the pressure of it decreases. So there's no longer this pressure of it pushing it back into solution. All right. So basic example, the basic point is the Henry constant is important connected to the temperature, and you use that with the pressure of that specific gas. So if you want to know for a specific gas, you need to have its partial pressure. For example, if there's a mixture, so like in air, you look at its partial pressure, or if there's a specific closed bottle, then you just need to get its pressure, and that's also dependent on the temperature. Okay, thank you for watching, and I'll see you in the next video.